let's see, where were we? We were talking about matroid polytopes. And one of the last things that we did was to draw the matroid polytope of our favorite matroid. And we found that it was a square pyramid. So the bases were, let's see, how does this go? 1, 2, 3, 1, 2, 4, 1, 2, 5, 1, 3, 4, 1, 3, 5. Okay. And in general, we said that the matroid polytope of a matroid was the convex hull of the indicator vectors of the bases. So when we fix that notation, I'm going to call V sub B the indicator vector for B. So it has ones wherever B has an element. So these entries are B. Okay. And so this is a polytope in our E. Okay. So PM is the convex hull of these guys, and remember I told you that there's two ways of describing polytopes, through the vertices or through the facets. And so the first thing that I want to do is show you that actually this is the vertex description. And what I mean by that is that actually all of these guys are vertices. Because so far we know that the polytope is the convex hull of these guys, but it could be that some of them are outside and some of them are inside the polytope. So I want to show that that doesn't happen. So proposition. Now I got the markers confused and I don't know what the good one was. That's better, huh? Yeah. Proposition. The vertices of the matroid polytope are all the V sub B such that B is a basis. So by the definition, we know that the vertices are a subset of these, but now let me show you that every one of these guys is a vertex. So if B is a basis, then the vertex, or the point V sub B maximizes. Remember that I said if I want to describe a face of the polytope, I have to give you a direction that that face maximizes. So if I want to say that this point V sub B is a vertex, then what I have to do is show you a direction that maximizes where V sub B maximizes in that direction. And that's pretty easy, actually. All you have to do is take this linear function. Okay. And that's pretty clear. So for example, in this case, these guys have 3, 4, and 6. So the linear function x3 plus x4 plus x6 takes the value 3 at this point, and for every basis, what this linear function does is that it only pays attention to coordinates 3, 4, and 6 and forgets the rest. This basis happens to have 1, 1, 1, so the total is 3, and the other bases don't have 1, 1, 1 here, so they have smaller value. And so that's it. The point V sub B maximizes this over over all v sub b's, and so it's a vertex. So that means that this is a complete list of all the vertices, and we actually need all the vertices to generate the polytope. Okay. So that's good for the vertex description. And my real goal for today is to show you, because basically the definition that I give you of the matroid polytope seems to be very vertex-centric. I define it as the convex hull of some vertices, but now I want to define, I want to find the inequality description. Okay. And so theorem, the inequality description looks like this. P sub m consists of the points in Re that satisfy a bunch of inequalities. So what inequalities do we have? Okay, well there's an obvious inequality that says that all the coordinates are non-negative. That's true of all the vertices, and therefore it's true of the whole polytope. There's actually an equality that says that if you add up all the coordinates, what you get is the rank of the matroid. Again, this is clear for every basis because every basis has rank of m ones. And if it's true of every basis, then that means that all the vertices are on this hyperplane, and therefore the whole polytope is on this hyperplane. And the other kind of inequality that I have looks like this. So this is for all I and E. And the other kind of inequality looks like this. For each subset of the ground set, the sum of the coordinates in that subset is less than or equal to the rank of the subset. Okay. And that's all that you need. So for example, if I take the subset, I don't know, 2, 4, 5, then the inequality here says that x2 plus x4 plus x5 is less than or equal to the rank of 2, 4, 5, which is 2. Right? And so this is basically what the inequalities look like that define this polytope. That's what we're going to show. Okay. That's our theorem. Any questions about the theorem before I prove it? I'm going to spend the rest of the class proving this, so now is a good time to ask questions.
Is the proof going to show us where each of these things
So
come from, or is the proof just going to?
yeah, so
is it an illuminating proof, or should I ask those questions now?
part of the proof is illuminating. Let me put it that way. So at least I will explain to you why these inequalities make sense, and they should be on this list. And what's a little bit trickier is to show that there aren't any more inequalities. But there are easy reasons why these inequalities hold. Okay. So in fact, why don't we start with that so that we can make sense of this. Proof. Let's call this polytope QM. And we want to show that PM and QM are actually the same polytope. Okay? And so the way you do this, as usual, is that you prove two inclusions. So the first inclusion that I'm going to prove is the easier one. Which is that the matroid polytope is inside here. In other words, it does satisfy these inequalities. Now, if I want to show that the whole polytope is in here, it's enough to show that the vertices are in here. And I say that the vertices of the P sub m's are the V sub b's, the indicator vectors of the bases. And so it's enough to show that each vertex is in here, because this Q sub m is a convex set. So if the vertices are inside this convex set, then the whole polytope is inside this convex set. So it's enough to show that each indicator vector satisfies these three conditions. First condition, B sub B sub I is greater than or equal to 0. Well, that's trivial because each coordinate of B sub B is 0 or 1. So there's nothing to say there, really. The third condition says summation of the coordinates of V sub B sub I. Well, as we said, B sub B looks like 0, 0, 1, 1, 0, 0, 1, 0, 1, 0. And if you add up the coordinates, you get the number of elements of the bases, which is the rank of the matroid. So there's no problem there either. The one that's a little bit trickier, but not too tricky, is the other one, which says you have an inequality. It's basically for any subset of the entries, let's say this subset. We call this subset S. What is the summation of the coordinates of the purple coordinates? Well, S is some subset from 1 to n. Okay? And the summation is basically the number of ones that you have here. And the number of ones is the intersection of the basis and S. So it's the number of ones, which is basically the size of B intersect S. In other words, you count this one and you count this one. They are the only two elements of the basis that are purple. Okay. But what can you tell me about B intersect S? Well, it's a subset of S, and it's independent because it's a subset of a basis. An independent subset of S can have at most rank S. It's an independent, and it's a subset of S, and therefore its size is at most rank of S. So that's why each vertex satisfies these conditions, and therefore the whole polytope P sub m is inside Q sub m. Okay. So I should call this maybe A. I had called it 1, but that's a little confusing because I put 1, 2, and 3 here. So A is going to be that PM is included in QM. And give me just a second, Chris. B, which I'm going to show now, is the opposite inclusion. And this will take some time. Okay. But so the point is really that these inequalities, there's fairly simple reasons for why these inequalities hold. And the question is, why are these all the inequalities that hold? Why don't I have other inequalities? What was your question?
Just making sure the last inequality is actually, or equality is kind of Oh, never mind.
He should get the C experience.
Yes.
Okay. Okay. So to prove this other inclusion that QM is inside P sub M, we're actually going to have to develop a little bit of theory. Theory that some of you may or may not know. We're going to need to talk a little bit about linear programming. Have any of you guys taken linear programming? Okay. So maybe this doesn't sound like linear programming just yet, but we'll see why linear programming is exactly the right tool that we need. And we'll see what linear programming is. It's another one of these things that sounds more difficult than it really is. What is a linear program? A linear program basically says, well, let me say it in words. Maximize a linear function over a polytope. That's basically what linear programming is about. You have a polytope, you have a linear function, and you want to find out inside that polytope what is the largest value that the linear function takes. Okay? So if I put it this way, then you see that this has a lot to do with what we're trying to do here. What is a linear program? You are given a matrix A. And let's say that it's a real matrix of size m by n. And you're given a vector in Rm and a vector in Rn. And let's see which is which. Little b is going to be a vector in Rm, and little c is going to be a vector in Rn. Okay. So given these guys, you're supposed to maximize this you should think of as the linear function. So your linear function is C transpose X. It's a linear function in Rn for X such that so this is the linear function, and this is the polytope. The polytope is given by a bunch of, if this is the first time that you're seeing linear programming or polytopes, you're used to equations: matrix times vector equals vector, ax equals b. Now we're going to consider the same thing, but just ax less than or equal to b, which says that the corresponding entries of this vector are less than the corresponding entries of this vector. And x greater than or equal to 0.
This may be totally obvious to everyone, but the first time I saw this, I had to get it through my head that x was a vector in Rn.
So x is a vector. So maybe I should say it here. For x is a vector in Rn such that, this is an m by n matrix times an m vector gives you an m vector. This m vector is supposed to be positive, and the linear functional is a function of m variables.
What is
This is transpose, C transpose. So if you prefer, you can think that this is the dot product of C and X. But the thing is that I'm thinking of A like this. This is A, it's an m by n matrix. B is a column vector of size m, and C is a column vector of size n. And X is also a column vector, so you cannot multiply C and X because they're both column vectors. You need to transpose it so that you get a 1 by n vector times an m by 1 vector. and you end up with a number, which is the dot product of C and X. So this is the definition of a linear program. Okay. This is the polytope. And we said that if you write down a bunch of linear inequalities, you get a polytope. And this is the linear function. Okay. The point of linear programming is that a lot of real life questions can be rephrased in this language. So many, and I mean many really, many real life questions can be phrased in this language, phrased as a linear program. And the great thing about linear programming is that there are very good algorithms. So there's either something called the simplex algorithm or the ellipsoid method are very good algorithms. And so the point is that in real life, people very, very often do this. They have some question about whatever, traffic, about connectivity of a network. There's really, any kind of system that can be modeled by linear equations and inequalities. You can write it in this way, and then use these two algorithms, and basically get very good answers.
What S dot dot.
What this means?
No.
What?
Second one.
Oh, sorry. Such that.
Yeah.
I just mean such that. So this is why people care about linear programming, and many different people care about this. And there's a very nice fact about linear programming, which is that it also has a notion of duality. So if this is a linear program, I'm going to tell you what the dual linear program is. This asks me to maximize this function over this polytope, and the dual linear program is going to ask you to minimize a related function. But this was a problem in Rn. So this lives in Rn, and this lives in Rm. And what you're going to do is that you're going to now consider this B your linear function, and you want to minimize B transpose Y for the Y's in Rm such that and so basically the roles of B and C are reversed. And the inequalities now look like A transpose Y less than or equal to C, actually larger than or equal to C, Y greater than or equal to 0. Okay. So whenever you have a linear program, you associate to it a dual linear program that looks very similar. You just change the A, B, and C around, and that's what you get. Now, this may seem very arbitrary to you, but the fact is that this is a good notion of duality in the sense that these are almost equivalent problems. So as soon as you have solved this one, you have solved this one, and vice versa. One thing I should say is that whenever you use the word duality, the idea is that the dual of the dual is the thing itself. So I define this guy to be the dual of this guy. But by that definition, also this one is the dual of this one. Okay. And so I'm going to fit linear programming duality in a board. So let me tell you what the duality theorem is. Yeah, sure.
So the C there is the vector C
The C is the same vector C in Rn. That's right. So what does the duality theorem say? There's two versions, the weak version and the strong version. Now, again, maybe I'll just make this. So again, this is the linear function you want to minimize here, and this is the polytope that you want to minimize it in. Okay. Notice there are some small differences. Here you're maximizing, here you're minimizing. Here the inequalities go in this direction, here they go in the opposite direction. Okay. The weak version of this says that any value of this linear function is less than or equal to any value of this linear function. So C transpose X is less than or equal to B transpose Y whenever X satisfies these inequalities and Y satisfies these inequalities. For X and Y, you call this feasible. And feasible just means that X is inside this polytope. So X is feasible if it's in here, Y is feasible if it's in here. Feasible means in the polytope. Okay. So any value of this linear function is less than any value of this one. And the strong version says that actually, if you have a solution to this, so if this linear program has an optimal solution, then the dual one does also, and the solution is the same. In other words, if this maximum value exists, then this minimum value exists and it's the same. So if U exists, let's see, how should I word this? People like to call this guy the primal linear program, and this guy the dual linear program. So if the primal linear program has an optimal solution U, then the dual has an optimal solution V, and the value is the same. C transpose U is equal to V transpose B. Now, what do I mean here when I say if the primal linear program has an optimal solution? Well, the question is, I give you a polytope, and I give you a linear function. Now, does that linear function have a maximum in the polytope? Well, it depends on the polytope, because maybe, for example, I might give you a system of inequalities here that has no solution. And if that's the case, then this guy, you cannot maximize this because there's no polytope here. And what this theorem says is that if that happens, then this guy is also empty. So I'm not sure if it says that this is also empty. I think what it says is something else. But the point is, if this guy has an optimal solution, then two things have to happen. this guy is non-empty, and it's bounded in this direction of C. Because you can also have polytopes that I mean, you can have system of equations that define infinite cones. And in an infinite cone, you might not necessarily have a maximum value. But what this says is, if you have a maximum value, then you have one here also, and vice versa. So in other words, solving the two linear programs are kind of equivalent questions. So that's linear programming duality in a nutshell. Of course, the proper way to do this is to spend a couple of weeks on it, but really, we're good. I mean, our application for this is very much, it's very kind of a pointed application, and so I've told you all that you need to know. And actually, we're not even going to use strong duality. We're only going to use weak duality, which says that any value of this linear function is smaller than any value of this linear function. And I should also tell you that the proof of weak duality is really, really easy. And maybe I won't do it because we don't have too much time. Not even sure we have time to do the rest of what I plan to do. So maybe what we should do is kind of take it slowly, and I will prove this, and then we'll stretch this out over 2 classes. I think that's a better idea. So let's go over here. Proof of weak duality. Well, so let X be feasible, meaning AX is less than or equal to B, and X is bigger than or equal to 0, and Y be feasible, meaning A transpose of X is bigger than or equal to C, and, A transpose times Y is bigger than or equal to C, and Y is bigger than or equal to 0. Okay. So I need to show this inequality that C transpose X is less than or equal to B transpose Y. Okay. Then C transpose X. I want to write that this is less than or equal to something. Well, I look at the inequalities that I have, and it seems like the only one that I can use is this one that says that C is less than or equal to A transpose Y. So C is less than or equal to A transpose Y, and therefore, if I transpose, I mean, remember these are vectors. So the ith entry of this vector is less than the ith entry of this vector. If I transpose, nothing changes. Okay. Now I claim that, well, so first of all, A transpose Y, remember transposed, you get Y transpose, A transpose transpose, which is A. Okay. Okay. Now I claim that I can multiply by X. Why can I multiply by X? The reason is exactly that X is greater than or equal to 0. And so, so basically you know that you can multiply inequalities as long as you're multiplying by positive numbers. Here you're multiplying by a vector, so you're just getting a combination of the inequalities. Okay, so C transpose of X is less than or equal to this thing. But now we see that we have exactly what we want. AX is less than or equal to B. And again, AX is less than or equal to B. And now I want to multiply by the transpose. And the reason I can multiply by the transpose is again, that the vector Y is positive. So if I combine this inequality and this inequality, I get that C transpose X is less than or equal to Y transpose B. And that's what I wanted. Maybe the last thing I should say is that Y transpose B is equal to B transpose Y. And why is that? Well, because it's just a one-by-one matrix, and so if I transpose it, I didn't do anything. Or another way of thinking about it is that this is the dot product of B and Y. So I take this inequality, and I get what I wanted. C transpose of X is less than or equal to Y transpose, and then E transpose Y. Okay. So that's weak duality. Now, maybe the next thing that I'll do is note something. Let's say that you have your linear program and your dual linear program. Okay. Suppose that you found X and Y feasible. So X is feasible in the primal linear program, Y is feasible in the dual linear program, and suppose that you found them such that C transpose X is, let me call them U and V. Suppose that you found them such that C transpose U is equal to B transpose V. Okay. What can you tell me about this situation then? So you found a U inside this polytope and a V inside this polytope such that the linear function on this point U is equal to the linear function on this point V. Well, if you have the situation, what you have just found is the optimal solution. The point being that this linear function is always smaller than this one. So if they agree anywhere, it has to be at the optimal place. Then U and V are optimal solutions. Because if you take X feasible in the primal linear program, then by weak duality, you get that the C transpose X is less than or equal to B transpose V, which is C transpose U. So for any X feasible, the linear function at X is less than the linear function at U. So U is optimal. And the same thing for V. Optimal means that it's basically what you're looking for. I mean, you're trying to maximize this linear function. Okay. So again, you have a polytope, you have a linear functional, and a point where that linear function is maximum is what you call an optimal point. It's the point that you're looking for to maximize this function. Yeah.
Suggest throwing up, if you throw just a two-dimensional polytope as a region, and a vector, so folks can sort of picture that, it might be helpful if you haven't seen it before.
Yeah, that's actually the next thing that I was going to do is just draw a picture so that this actually becomes more concrete. Maybe we'll do that and then we'll delay the proof of this for next time. So let's see. I'll take one.
Okay. So what if you let your vector and let your matrix A be 1, 1,
In which direction?
rows.
1,
1,
1,
1, 2, 1.
2, 1.
And B is 10, 15. And C is 3, 2.
Okay, so let's see what this looks like. So the primal is this guy. What are the inequalities? AX less than or equal to B, right? So 1, 1, 2, 1 times XY less than or equal to 10, 15.
Like one more suggestion.
Yeah?
Make them x1 and y1, x1 and x2.
X1 and X2. So, and X1, X2 bigger than or equal to 0, 0. Okay. So what do these look like? Well, this is X1 plus X2 is less than or equal to 10. 2x1 plus x2 is less than or equal to 15. x1 positive or non-negative, x2 non-negative. Okay. So let's draw this. x1 plus x2 less than or equal to 10 is a line like this. Right? It goes through 10 here, and say 10 is here, and 10 is here. And so the first inequality says you're over here. x1 plus x2 is less than or equal to 10. 2x1 plus x2 is less than or equal to 15. So this is 10. This is 10. That one goes through 15 here, and it goes through 7.5 here. So that looks like this. And the inequality 2x1 plus x2 is less than or equal to 15 says you are over here. And then these inequalities, x1 bigger than 0 and x2 bigger than 0, say you're in the first quadrant. So then, what is the polytope here? Well, it's exactly this quadrilateral right here. Okay, and so what is the linear program asking us to do? Is asking us to maximize this linear function over here. So goal is to maximize 3, 2 transpose. So that looks like 3, 2 times xy, which is 3x plus 2y. What does that look like? It is a line, 3x plus 2y. I'm sorry?
Doesn't matter. 2, 3 would be slightly better. That doesn't matter.
Okay.
Doesn't matter.
So 3x plus 2y. Now I have to, okay, so, you can think of it as this way or as drawing the arrow, right? And the arrow points in the direction 3, 2, which is something like this. 3, 2, like this. This is C. So actually, easier than doing this numerically, you can look at the picture and say, if I'm pointing in this direction, then what is the optimal point in this direction? Is it this one or is it this one? And you're kind of pointing in this way. Is it, well, maybe it's not so clear. But that's what the linear program is asking me to do, is here's the direction. What is the highest value of that linear function here? Highest value for 3x plus 2y inside here. We know that it's going to be at a vertex, and it looks like it's either this vertex or this vertex. It doesn't look like it's from the direction, but anyway, it's surely one of these three vertices. And if we had a good picture, then we would know. I'm sorry?
Because we know what that vertex is, we can just check it? Is that what you're saying?
But yeah, the other thing we can do is just basically find this point and just check those three vertices.
So, and if two of those points, say the one in the middle and the one on the bottom, were the same, then it would actually be the whole face. Right?
Or it could be a whole face, yeah, possible. Okay. I'll leave it as an exercise for you guys to do this because we're running out of time and I want to show you the dual program. For the dual program, I have A transpose is this, B is still this, C is still this. Well, I won't write them again. And so the dual program says you want to minimize 10 x1 plus 15 x2 in the polytope. What are the inequalities? Now I have A transpose Y bigger than C. So that looks like x1 plus 2x2 is bigger than or equal to 3. x1 plus x2 bigger than or equal to 2. x1 bigger than or equal to 0. x2 bigger than or equal to 0. Okay. So what does that look like? Well, like x1 plus x2 bigger than or equal to 2 is, here's 2, here's 2, and it looks like this. But now it's telling me to be bigger than or equal to 2, so it's actually pointing in the other direction. x1 plus 2x2 bigger than or equal to 3. So that goes through 3. That goes through 1.5. I'm just going to draw a bigger picture. Just remember that there are different scales. So here's, what did I say? 2. Here's 2. Just like that. And then here's 3. Here's 1.5. Just like that. So it's telling me to go over here, and then above here, and above here. So what's my polytope now? It's this thing over here. Which is unbounded, and that's the issue here. And I guess the way that I defined polytope last time, I defined it to be bounded. And really the proper word here is polyhedron because it might be some unbounded thing. What's my linear function? Well, it points in the direction 10, 15, which is something like this. 10, 15, so it's like this. This is my linear function, B. And so now what you're looking for is the lowest vertex according to this linear function, which again, it looks like it's either this one or this one or this one. So the exercise that I'm going to ask you guys to do is to either draw a good picture and see which one it is, or just find the coordinates of these 3 points and see which one it is. And the same here, find the coordinates of these 3 points and see which one the optimum is. But what I can guarantee you is that if you do this correctly, the maximum value here is going to be the same as the maximum as the minimum value there. And this is what linear programming duality says.
It's not that the point will be the same point, it's the value when you multiply them by the same.
That's right. So it's not the point itself, it's the value that's important. So what I was claiming here is that the value of the linear programs, the optimal value of the linear programs is the same. Not the point where they're, not the optimal point, but the optimal value. Yeah. Yeah, actually, this is a very good exercise. Thanks for thinking of some good numbers. And so please do this, and then next time the discussion will be a little bit more, you'll have a better picture in your head of what I'm actually going to say next time. Okay?
This recap was actually great for me. Like, it was like, it gelled a bunch of things that were floating around all over the place. But the fact that it was gelling them for me, didn't force you had to be in the report. It might not gel.
Yeah, this is something. Some of these things that I said, it's not very difficult conceptually, but it's just something to get used to.
Yeah, you just, I mean, there are even little things that, for whatever reason, particularly having taught algebra, taught high school algebra for a long time, when I see an x, I think a single variable. It's taken me 2 years of graduate school to see an x and think it might be a vector. You know, and even here, like, you know, when we did x1 and x2, and then they became x and y again for you as well. Like, in some funny level, like,
Oh, yeah.
they have this, they mean, you know.
Yeah, but then, so what people do is draw little arrows and they kind of so obnoxious you can't see it.
No, it's not helpful. It's just sort of helpful to clarify, like, I mean that little numbers.
It's like psychological hurdle. Yeah.
The other thing, wait, before you erase this picture,
Thank you.
that's kind of neat to do here is, so this guy, you probably, this has slope
Yeah, I did.
-1, and this has slope -2. And this guy has slope -3/2. And so you know that
What did you guys
maximize that.
talk about Wednesday?
Because what you're really doing is maximizing a lot.
Just a pinch.
I'll check it tomorrow.
Okay.
Exactly. So that's how you can construct one of these fast to get
All right.
somebody who doesn't hit one of these 2 points.
Federico, are you going to be in your office from 2 to 3 today?
Yeah.
Awesome. Can I come by?
Yeah.
Yes, thank you.
I'm substitute for.
Oh, right, so
Amanda.
you're-
You know, Kim, actually, I think that when I learned this, I never even drew this picture.
What, you didn't know this picture? You just
I mean, I knew it, I've seen it, but only like, yeah, I think when I took this class, I never bothered, like, oh, here we go. Proof.
You know why? It's because my 7th grade teacher taught it to us in the 2-dimensional version.
Oh, wow.
So I got it way back then,